Chapter 9. In science, a wave is a disturbance. Unlike most waves, electromagnetic waves can move through space. All periodic waves can be constructed from the most fundamental wave, the sine wave. The sine wave function in trigonometry is the ratio of the opposite side of a right triangle to the hypotenuse. The sine wave is the shape of the trigonometric sine function plotted as the amplitude as a function of the angle. It is the projection of a vector rotating at a constant rate. Example, this vector here is rotating through this circle. As it rotates, it traces out this sine wave. At each point, if you drew down a vertical line to the zero, you would get the same distance on the sine wave. So as this wave moves, it plots out each angular measurement, and you can go all the little ones in between, and that plots out the sine wave. The radian is the angle that is formed when the arc is equal to the radius of a circle. There are 2 pi radians in one complete revolution. So this sine wave, it ends at 2 pi. The x crossing is at pi and 2 pi for radians. Because there are 2 pi radians in one complete revolution and 360 degrees in a revolution, the conversion between radians and degrees is easy to write. To find the number of radians given the number of degrees, you take 2 pi radians divided by 360 times the degree, or it's just pi over 180 degrees times the degree number you're given. If you're given the radian number, you want to take 180 degrees over pi and multiply by the radian number that you're given. So the conversion is either pi over 180 or 180 over pi. Electrical waves with the same shape as the sine function are also called sine waves. The electrical sine wave is characterized by the amplitude and period. For example, the peak voltage of this waveform is 20 volts. The period is 50 microseconds. So how do we get that? Well, right here, the peak voltage is at 90, which is right here, and if you go over, it intersects at 20 volts. So it has a 20 volts peak. It goes all the way down to minus 20. So the peak to peak, if I was to draw that here, peak to peak would be 40 volts. 20 volts peak, 40 volts peak to peak. And the period is the length of the positive and the negative. And right here, this is in microseconds. So the complete period is 50 microseconds. The voltage can also be specified as either the peak-to-peak or the RMS value. So I just showed you the peak-to-peak. Now the RMS value is equal to, which is a standard formula, 0.707 times the peak value. So if the peak value is 20, we just take 0.707 times 20, which is 14.14 volts RMS. Now the RMS value you'll read on your digital meter. The peak and peak-to-peak values along with the period is something that you read on the oscilloscope. Period and frequency. There's an inverse relationship between period and frequency. Frequency is 1 over the period and period is 1 over the frequency. Thus, if you know one, you can find the other. For example, if the period is 50 microseconds, the frequency is 0.02 megahertz or 20 kilohertz by moving the decimal place over 3. So here, all we're doing is taking 1 over 50 microseconds, and that comes out to 20 kilohertz. The sine wave equation, the equation for the instantaneous voltage of a sine wave. So here we have the instantaneous voltage is equal to Vp times the sine of theta. And theta is any angle that you're looking at. So in this example here, they're taking 25 volts peak times the sine of 50 degrees. So on your calculator you put 50, press the sine key, and then multiply by 25, and you should get 19.2 volts. So what that means, if I trace out the sine wave, this is my 180, this is 90 right here. 50 degrees is probably right around here, so we're looking at that point right there, which if this had a peak value of 25, that would be approximately 19.2, which they show you right here. A plot of the example is shown here. So they're also showing you how you do it in terms of a vector. So if you're in the coordinate plane and you plot out 50 degrees, you draw the vertical line down from the peak. This distance here is the peak distance, which is 25 in this case. And if you follow that over, for this distance here is 50 degrees. That point there would be at the 19.2. Phase shift, example of a wave that lags the reference. The reference wave is always the wave that starts at 0. Now, by just looking at this, you would think that this is, to check to see how this is working, you have to look at the peak values. Whichever peak value occurs first, that's the one that's leading. So it's opposite of what you would think it is. So this one here is leading, this is lagging, even though it looks like it's ahead of it, but its peak value is occurring after it. So this is lagging. And leading. So here again, here's the reference wave still at 0. This now is occurring first. So the red line now is leading. The blue line with the reference wave is lagging. So the equation for leading is plus the phase shift. You still put the angular measurement in theta, but this here is this distance of the phase shift. And for this one here, which they didn't give you the formula, it's equal to Vp times the sine of theta minus the phase shift. Ideal pulse. An ideal pulse looks like this. It has an amplitude, which is the maximum point. It has a leading edge. It has a falling edge. Baseline is down here. And this distance here is the pulse width. This is a positive going pulse. A positive going pulse starts at a lower baseline and goes up to the amplitude. This is a negative going pulse. A negative going pulse baseline is up here and goes down, but all of the other definitions are the same. A non-ideal pulse. Non-ideally, the pulses do not go straight up, across, and straight down again. There's a certain amount of time that it takes for the pulse to get to that point. So the rise and fall times are measured between the 10% and 90% levels, so this would be 10%, 90%, where the pulse width is measured from the 50% point on each wave.